Alrighty, welcome back. If you are following along with the, calendar on the syllabus, you should be watching this on Monday, 12th. You would have an exam on Thursday. So this is one of the last sections, not the last, just the second to last. So 2.6, getting information from a linear model. So chapter 2, we've just been looking at linear models. We learned different ways to write letters. I don't know why Duke is now deciding to play. Different ways to write the equation of a line. And in chapter 1, we even talked about making real world functions and stuff like that. So now we're gonna kind of mold the two together. All right, I like this chapter. I think it's fun. So we can learn a lot from looking at linear models. Let's look at these examples and see what different models could tell us. Excuse me. So a swimming pool is being filled with water, right? So let's just draw a picture. That's our above ground swimming pool, and I'm filling it with water, right? So this is going up. All right, so a linear equation of y equals 200 plus 5x models the volume in y. So y volume in the pool at time x. Okay, x is time. I like to write what we have and what we want. So we have that y is the volume, x is time, and I have that y equals 200 plus 5x. If the pool has a capacity of 10,000 gallons, when will the pool fill? So I want, it's also a good thing to kind of say what y and x are, because it gives you a clue of which variable you're going to solve for when asking this question. So if the pool has a capacity of 10,000 gallons, when will the pool fill? So I want x when y equals 10,000, right? I want to know the time at which my volume is 10,000. So that's another way of thinking about it. Okay. So I have this equation y equals 200 plus 5x. Okay, that gives me two unknowns, y and x. So I set one unknown to 10,000 because that's what I'm interested in. So instead of y equals 200 plus 5x, I'm going to do 10,200 equals 200 plus 5x. And we're going to solve for x. And I think we're pretty good at solving for x by now. So minus 200, give me 9,800 equals 5x. And then we're going to divide. So x is going to equal, I don't know, divided by 5. So that's exactly what I'm putting into my calculator. 9800 divided by 5 is going to give me 1,960. So 6. Are we ever given units? I'm given gallons. I'm not given at a time x. I don't think we're given units at all. Let me see if I gave myself units. This is where I would kind of assume, I really would hope it wouldn't take that many hours. It's probably not going to take that many seconds. But let's just call it minutes. If you're not given a time unit, but you know it's time, just make one up. I'm kidding. Don't do that. You're always going to be getting units. Just this time I forgot. Okay. Cool. Ta-da. And that was problem 1. Okay, cool. So that was, I was just given a linear model. Great. But sometimes I'm not going to be able to really, what did I want to say? I'm not going to be given a linear model, or maybe I'm not going to even just given it's not even going to be a linear model. Just pieces of it are going to be linear, right? So something that looks like y mx plus b is going to be somewhere involved. All right, so how to construct models that lead to linear functions. Okay. So how exactly can we construct a model? We talked about in 1.8 that there's no really set way to come up with these functions. It's a lot of practice and taking knowledge from other various things in life, knowing what perimeter of a shape is and area of a square, something like that. And then if we are given two equations, one has to be set equal to another and blah, blah, blah. So these ones have a set way in your textbook, which is really nice. So how exactly can we construct a model? So first we're going to choose the variable, which kind of seems a little wacky. So choose the variable, right? So identify the varying quantity in the problem, the independent variable, and give it a name, such as x. It doesn't have to be x. If it's time, use t, whatever. Just keep it consistent. Kind of like how I said, we have y dash volume, x dash time. I do that in problems all the time. So like it's not, I wasn't just doing that for you guys. I was doing it for me. Because that's how I do problems. So it's really useful to kind of just, what's varying here? Is it volume? Well, that's varying, but that volume depends on the time because I'm filling it up, blah, 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 blah. Time is always an independent variable. No man can control time. Colon or in between. So translate words to algebra is our next one, right? So and if this seems all like kind of crazy right now, obviously we're going to do some examples and we'll talk about each step. Oh, and sometimes in the problems you're going to be given like make this your independent variable, right? So express all quantities given in the problem in terms of the variable x. So this is where we'll talk about maybe like this thing plus this thing. So it'd be like thing one is going to be like 2x plus 3 and something like that and so on. That would be a way of translating words to algebra for like a certain part of a problem, right? Because it's like models that lead to linear equations, right? So it might not be linear right out of the box or look linear. All right, and then the last one is to set up the model. So putting all the pieces of my model together. Oh, did anyone play with Bionicles growing up? Probably not. My stepbrothers did, and they always looked really cool. And so when I hear set up the model, I think of Bionicles. Okay, express the model algebraically as a function of the variable x. So just taking those bits that we got from 2, so those little like translated verbiages, sentence things, expressions, thank you, and then put them into the model. All right, so that just sounded like a bunch of hoo-ha, so let's do a problem where that makes kind of more sense. So Mary inherits, oh, I always wrote this problem wrong. Mary inherits $10,000, great for her, and invested in a 2-year certificate. Deposit. One certificate pays 6% and the other pays, I don't know why it's a simple interest, but it's 4.5% interest annually. All right. A certificate of deposit, basically, it's not like a stock or anything, but basically, oh God, like I remember someone's like, oh, I have bonds. Or someone like paid for, I don't know, I remember having like a $50 certificate from somebody. And they appreciate over time and it's very slow. But it just has a set end, basically. They're not very common, but they're common in math problems because they're easy to talk about. All right, so construct a model of the total interest. So I also like to highlight things when we're doing them. There we go. So total interest Mary earns in 1 year on her investment. If you don't know about interest, right, so it pays 6%. So whatever she puts in, she'll get an additional 6% every year. So if she keeps at 6%, then she'll have 100,000 plus that 6%, she puts it all in that part. And then what else? After that 1 year, she'll get another 6% off of the total. So like $160, right? 100,060, 600, maybe 600. Okay. Anyways, so she has one certificate that pays 6% and the other pays 4.5% interest annually. So let's call Cert A the 6%, and we'll call certificate B the 4.5%. Okay. So she's putting, this question isn't clear. She's putting amounts into each of them. So she's going to split up how much she is going to put into certificate A and certificate B from that $10,000. So our first step is to choose the variable X. So, actually I want to move this over here. Duke, it's okay. Excuse me. So I'm going to say let X represent, what do you think is going to be the varying thing? It's the amount of money that we put into each account, right? That's going to change how much I get out after a year. So let X represent the amount of money in the certificate that pays 6%. It doesn't have to be this one. It could be the 4.5 one. It's kind of good to state that though, sometimes, so that you can not switch your variables halfway through and get confused. Okay, so let's pay 6%. I think we call that one Cert A. So X would equal the amount that's in certificate A. And she's going to invest all of her 10,000, right? Mary is fine right now. So she's like, I don't need it for this year. So let me just make some money on it. So we can say like thus what is she doing? She'd put 100,000 minus X into Cert B, right? The 4.5%. So if she's going to put X amount into A, she has 100,000. So the leftover is going to go to the other one, right? So this is kind of what I was saying about putting, what is it called? Like taking things from the outside world that I haven't necessarily taught you guys. So interest rate, 6%, that's how much I'm going to gain. So so let's say interest, that's not how you spell interest. Oh, it is interest. Okay. Interest of Cert A is going to be however much I put in, it's just the interest. So I'm just going to gain 6%. So I can't write 6%. That doesn't make sense. I have to make it to a decimal. So a percentage out of 100. So you do like 6 divided by 100, which is 0.06. So 0.06. And then similarly, so it would be, right, this is our amount times our interest rate. And then the interest of Cert B, our amount is, I have to put it down here, 10,000, 000 minus X times 0.045. Okay. So, but I want to find my total investments. So my total, I'm like really writing this out for you guys. Total investments. Let's call that T. That's going to equal investments from A plus investments from B, certificate B, the 4.5% one, right? So I'm just going to take, this is kind of what I was saying by like expression or like blurbs. I'm going to take this one. That's my investment for A. So X, let's write it like this. Oh my God, I have a tickle on my nose. I thought I was over my cold yesterday. And so I stopped taking like Mucinex and Sudafed and it's not gone. Minus, no, not minus, plus our investment from B, which was, oopsies. No, I can write it like that. 10,000 minus X times 0.045, right? And that's our model right there. So that was step 3. So you're like, it doesn't look like a linear model. It's like y equals mx plus b. Remember, we just need x to be to the first power and then we're fine. And you can distribute that if you want. It doesn't quite matter right now. All right. So that's our model, right? I cert A and I cert B, 6% and 4% respectively. I just did that to save time on writing. And then we chose X to represent the amount that goes into the 6% certificate A. And then that implies that since I have $100,000, excuse me, 100,000 minus X is going to go into the other account. So then I find the interest for each certificate, and then I want the total interest, so I'm going to add them together. And that's how we made our model. All right. So if Mary invests 5,000, oh wait, if her total interest is $5,025, how much money did she invest into each certificate? Each certificate. This is why it's important. So total interest equals this. How much money did you invest into each certificate? So we'll be like, certificate A should put in that amount. Certificate B should put in this amount. It's kind of like when I ask you to mention something, I need X and Y. I need 2 things. All right. So her total interest was that much. So T, that's our total. I should have said interest, not investment. What am I thinking? Interest. That's going to know my total interest. I spelled interest wrong. Interest. You think I would know since I worked at a bank collecting interest from big companies. So I'm paid late. All right. So our total interest. So T, I know T equals 0.5025, and I want X and 10,000 minus X, because those are the amounts that I would have put into each account. Jesus. So we're going to set 5,025 equal to 0.06X plus 10,000 minus X 0.05. And we're actually I'm going to distribute that 0.045, just make our life a little bit easier, because I want to combine all my X's together. So 0.05 times so this is 4,500 minus 0.045. I think this is going to 0.025. Right? Let me just check that, because something with decimals always. Okay. See, I did that wrong. Plus 4500. Okay, great. So I just distribute my 0.045. The reason I write 0. Something system extension is not capable of max. Please connect all. Frick does that mean? Okay, well I hope everything's fine. Weird thing on my screen. Okay. So now we're gonna solve for x, okay? So minus 4500 minus 4500. So I get 525 x. And then when I divide everything by 0.15, we'll get that x equals 35,000. So remember, I want to know how much she put in each account. So we can say, cert A, write the 6%. She put 35,000. Right, and then I'll need to do like 10,000, 100,000. I don't know why I keep saying 10,000. 100,000 just seems like a wild number to me. I think that's going to be 65. Yeah, so then cert B. And there you go. Ta-da! So yeah, just remember to read the questions very carefully so you know what you need to tell them, okay? Okay, oh, fun. I love this one. Okay, so this is a little background that I'm giving you. The book also talks about this. And if you've ever taken a chemistry class, you might know. But if an amount X of a substance is dissolved into a solution of volume V, then the concentration C of the substance is C equals X over V, right? So that would be like the concentration, my amount of whatever the concentration I want to know of. If you think about like concentration of fruit juice, 6%, that means that 6 milliliters out of every 100 milliliters is juice, right? Over whatever the volume is. So that's what we think about concentration. It's some division, okay? When I talk about, that's like a liquid though. So you have the volumes add up. If I have like a total volume, right? If I'm adding like various liquids for a good time together, the volume is going to add up the more I put in. But if I just put in like sugar into my lemonade, my volume isn't going to change much. It gets dissolved. Probably increases just a little bit. All right, so, here we go. So if 10 grams of sugar are dissolved in 5 liters of water, this is coming up. This is not just changing weights. There's a reason for this. So you can do more problems with linear things inside of them that have to deal with the division. So if 10 grams of sugar are dissolved into 5 liters of water, the concentration is, right, so I'm putting, you're not going outside right now. The concentration would be my substance over my volume. So 10 grams over 5 liters, which would reduce to 2 grams per liter. That would be my concentration. All right. So speaking of orange juice, or like something has such amount of fruit juice in it, a manufacturer of soft drinks advertises its orange soda as naturally flavored, although the soda only contains 5% orange juice. I like to highlight all numbers. A new federal regulation stipulates that to be called natural, a drink must contain 10% fruit juice. The word natural on food actually has no stipulations to it right now, most of them. To be something to be local, it just needs to be within 200 miles, which is crazy. It doesn't seem local. The manufacturer has a 900-gallon vat of soda. Sounds great. And decides to add pure orange juice. I'm highlighting this. Oh, add, because it has the word add in it. To the vat. All right, so construct a model that gives the fraction So my model is going to be a fraction. Okay. Of the mixture that is pure orange juice. Okay. So what's the thing that I'm varying? If I have a 900 gallon vat of soda and I'm adding orange juice, the thing that I'm varying is the amount of orange juice, right? So let's do X equals, if this is gallons, it's probably going to be gallons as well. I don't want to talk about cups versus gallons. That's confusing. God knows the US measuring system is weird. Okay. So X is going to be gallons of orange juice. Okay. So now we're going to change. Okay, so I have 900 gallon vats of soda that, and it already contains 5% orange juice. So if I want a fraction of the mixture that is pure orange juice, okay. What do I need? So let's call this C of X. So total, the top is going to, so the fraction of mixture that is pure orange juice. So that's like the concentration of pure orange juice. So my amount of pure orange juice over my volume. So total gallons of OJ, and it says pure orange juice, so you're not thinking like orange soda. It's like 100% juice, okay? And then over the total liquid in the tank. And I don't just write 900 because if I have a 900 gallon vat of 5%, I want to add, I'm adding pure orange juice. So I actually had an example of orange juice and I drank it. That would have been really smart. But if I only have wine over there, I can't use that. I'm adding more into it. So the volume's going to grow with the amount that I add. Okay. So my total gallons of OJ, each of these things are going to be a linear model. Okay, linear model. Those are the only models that we know how to make. So really, kind of. At least in this context, right? So total gallons of orange juice are going to be my initial plus whatever I add. So the total number of orange juice in the vat is going to be what was already ever in there plus what I'm adding on top of it. Okay. So my initial amount of OJ, my 900 gallon vat is 5% orange juice. So 0.05% of 900. And then how much orange juice am I adding? Well, I deemed that X. So this is just going to be plus X. I don't know what this number is. 45. So 45 plus X is going to be the total gallons of orange juice that are in the vat when I add X amount of gallons. So 45 already, and then whatever amount I pour in is going to be in there. Okay. Total liquid in the vat is also going to be a linear model, right? Right. That's going to be my initial volume plus I'm only adding OJ, so it's going to be plus the OJ added. Okay. So I start with 900 plus X. So now I'm going to put them together into my concentration, and it's going to be 45 plus x divided by 900x, 900 plus x, excuse me, right? And that's from this top bit up here. Total gallons of orange juice divided by total liquids in the vat. Okay, so great, I did it. We did it. That is our model. Is that all we're asked to construct a model? Okay. We could also constructed a model that was not orange juice, the concentration of non-orange juice. Okay. That's another thing you could have been asked, that not inverse, but like complement. There we go. Okay, so how much pure orange juice must be added for the mixture to satisfy the 10% rule? Okay, cool. So 10%, remember we need to talk about things in decimals. So I want my concentration. So how much pure orange juice do I want? X when my concentration equals 0.1. Okay, so 0.1 is going to equal 45 plus x divided by 900 plus x. A good rule of thumb for these problems too is if I'm adding liquid to another liquid, the denominator is always going to be changing, right? It's not going to be staying the same. Same if I'm taking liquid away. Okay, so everything times 900 plus x, 45 plus x. Oh god. 10% of 900, is that just 9, I think? No, it's 90. Yeah, 90 plus 0.1x. Don't forget to distribute both. All right, so then we'll do minus 45, and then minus 0.1x. So that's going to give me 45 equals 0.9x, because you can think about that as like 1x. So divide by 0.9, divide by 0.9. Okay, so x equals 50 gallons. So how I solve this problem, right? So plugged in that value for c of x. I want everything on the same playing field. So right now, 900 plus x was in the basement, so I brought it up top. So we got this, and then I distribute my 0.1 because dividing it wouldn't do anything. And then I get everything that has x on to its own side and everything that doesn't have x onto the other side. And then I want x alone, so I divide by 0.09, and that's how I get 50 gallons. So we need to add 50 gallons. Okay? Really great. And if you, sometimes I like to pose the question of like, what amount would you expect if we're at 5% and we had 45 gallons? How much would I need to get to 10%? And people are like, oh, another 45, I'm doubling the amount. No. Because when I do that, you're not thinking about the change in the volume on the denominator. So it's not going to be like 1-to-1. So I need to, if I want to double it, I need to also consider what's happening in the denominator because it's moving as well. I'm adding liquid to the top and to the bottom. Okay. So that's why it's 50 instead of 45. All right. So I think this is our last problem. Okay, cool. Then Duke's going to the vet. All right, cool. So Al paints with watercolors on a sheet of paper that is 20 inches by 50 inches high. Okay, so There we go. So this we'll call 15 and this we'll call 20. Oh my God. Okay. He then places the sheet on a mat so it is uniformly wide. Okay, let me put the 20 on the inside. That a uniformly wide strip of the mat shows all around the picture. Okay. So then we have this mat. Let me just draw a rectangle instead of all these lines. Great. Something like that. Uniformly wide here. Yeah, okay, it's never gonna be perfect, but whatever. Uniformly wide, what we mean by that is that this distance is the same as this distance, just the same as this distance, it's the same as this distance. All right, and those are just question marks because we don't know what it is yet, and I don't know if it's varying or not. All right. He put blah, blah, blah. Construct a model gives the perimeter of the mat. Whew, okay. Perimeter of the mat. So this sheet of paper, it's not changing at all, right? The gray piece of paper. What's changing is how big this mat is. So instead of thinking about like the mat as like length and width, let's use something that we already know. So we want to find perimeter. So instead of calling it like the perimeter, this would be wide and this would be length. Yeah, instead of calling the perimeter like 2W plus 2L and having these two things, let's use that this length is the same all the way around and that it has to be at least 20 and 15. If it's smaller, then we kind of silly to put a map behind a painting, right? So my width, so let's call it X is going to be the width of the mat around the picture. So like this would be X, right? This distance. All right. So my width is, I know it's gonna be 15, and then it's gonna extend X onto one side and X on the other side. So it's gonna be 15 plus X on one side plus X on the other side. So 15 plus 2X. Right. Additionally, my length is gonna be kind of the same thing. It's gonna be 20 plus this other length plus this other length, right? Because we're trying the perimeter of the pink one. I should have written this in pink, but whatever. So it's going to be 20 plus X plus X. So 20 plus 2X. Great. So that's the length and the width, but I want to construct a model that gives me the perimeter. So the perimeter is going to be 15 plus 2X. Just plug it into my perimeter equation. 20 plus 2X. And if you wanted to, we could go ahead and do like 30 plus 4X plus 40 plus 4X, which is going to give us 8X plus 70. Which again, if you kind of think about that, that's where our initial perimeter, if I just don't have the mat, is going to be the picture. And then for every uniform I add, that's the perimeter getting bigger. Okay, so that is the perimeter. So if the perimeter of the mat is 110 inches, how wide is the strip showing? Okay, so I'm not, X was the amount of was the width of just that little bit that's showing. Where's my highlighter? So my perimeter is 110 inches. How wide is the strip showing around the picture? Okay. You could have also been asked, how wide is the mat? and you have to go from there, okay? So 102 is my perimeter, so that's gonna equal 8x plus 70, minus 70, minus 70. So 32 equals 8x. So 32 over 8, is that 4? Remember, I had to stay after school for my 7 and 8 tables, so I'm not very good at them. Okay. X equals 4. And since this is in inches, I'm also going to assume that that's also going to be in inches. I'm not changing anything. So 4 inches. Okay. I think this section is pretty cool. Using linear models in different ways and different bits and putting them together, adding them together, dividing them, and so on. So I think that's pretty cool. Alrighty, so that's all for today, because this is kind of I think a very big section concept-wise. So I will see you guys tomorrow.